All right, here we got the notes for section 2.3, polynomial functions of higher degree with modeling. So you're going above the squared. So a couple definitions, vocabulary for polynomials. So each monomial in the sum is a term. So 2x squared, 7x, 4, they're all the terms. Polynomial function written in this way with terms in descending order is written in standard form. So standard form has highest exponent first and then counting down. The constants, so the a's in this formula, are the coefficients. The coefficient of the highest power term is the leading coefficient because it appears in the lead when you write in standard form. And a0, the last term, is the constant term. It will not have an x in it. If you notice, the subscript here matches the exponent. So if this was an x to the 7th, this should be a7. Now, it's entirely possible that you don't have all of the terms. Like, just because you have a x to the 7th doesn't mean you have to have an x to the 6th, and so on and so forth. Okay, so example 1, describe how to transform the graph of an appropriate monomial function into the graph of the given function. So you've got, so this guy here is based off of x cubed. So in the parentheses is a left-right shift, so this graph is going to have to go left 1 unit, and you've got a vertical stretch of 4. So typically, cubic function, the key points are there, there, and there, and it kind of stretches out. 2, 8 also appears, as does -2, -8 down there. But if I move everybody left 1, I should do the stretch first, so everybody multiplies by 4. So this point is going to go, instead of being at -1, it's going to be at -4, but it shifts left 1. So I've got a point there. 0, 0 doesn't stretch, but it does shift left 1. And this point here that's at 1, 1 will stretch to 1, 4 and go left 1. So this graph looks something like that. So if you notice, I got my so it talks about compute the location of the y-intercept. So that y-intercept occurs when x is 0. So if I plug 0 in for x, I get this, which is 4 times 1 cubed. So exponents first, so that's 4 times 1, which is just 4, which is the value that I did get. So over here, we've got x to the 4th. So let's see here. This one is kind of a steeper parabola, for lack of a better word. So 0, 0, 1, 1, but instead of 2, 4, it would be 2, 8. No, it's 2, 16, we can cube it. But anyway, this guy's going to go up 5, right 2, and reflect across the x. So the vertex should sit here at 0, 0, but it's going to go up 1, 2, 3, 4, 5, and right 2, 1, 2. So there's 1 point. So then for a cubic, x to the 4th, sorry, what this guy's based off of, 1, 1 would appear, but 1, 1 has to go up 5 over 2, but then mirror, so it's going to be here, here. So this graph looks something like this. If you notice, I just drew it narrower than a standard parabola. Actually, plot intercepts. But if we want to find the intercept, so that's plug 0 in for x, so that becomes this. So this is -2 to the 4th plus 5. So -2 to the 4th is -2 times -2 times -2 times -4, which is 16. So this is -16 plus 5. So this is -11. So I didn't even draw my graph steep enough because it should come way down here before it crosses. Alrighty, moving on to example 2. It says graph the polynomial function, locate its extrema and zeros, and explain how it's related to the monomials, from which it's built. So let's see here. Let's just do a t-table. So for x, so our y value is x cubed plus x. So let's start at -2. We'll do 5 values. So if x is -2, that's -8, so that's -10. If it's -1, that's -2. If it's 0, it's 0. If it's 1, it's 2. If it's 2, it's +10. So those are my values. So I'll plot those points. So -2, -10, be way down here. -1, -2 would be here. And then we've got 0, 0. And then we've got 1, comma 2, and then we've got 2, comma 10. So it looks something like that guy. So extrema means if there's any max or mins. So for this guy, this extrema, there are none, because this graph goes up and down forever. For the zeros, that's where it crosses the x-axis. So that would be at 0, comma 0. And how it's related to the monomials from which it's built. So as you get farther away from the origin, it looks like x cubed. But as you're close to the origin, it looks like the line y equals x. So that's what it means by close to and far from. So for the second one, we'll do the same thing. So t-table, x cubed minus x. So we'll use the same values just to see how they compare. So same values. So if x is -2, that's -8 minus -2, so that's actually -6, because it's -8 plus 2. For -1, I get -1 minus -1, so that's -1 plus 1, which is 0. 0 is going to be 0, 1 is going to be 0, and 2 is going to be 8 minus 2, or positive 6. So if you notice, I have these three values, so this graph's going to be a little bit trickier to figure out. So -2, -6, -1, 2, 3, 4, 5, that's the right point. -1, 0, 0, 0, 1, 0, and 2, comma 6. Now, so here's the thing. In order to get through all of these points, so they're trending up as I go left to right. So, but that means this graph has to turn around. So it has to do this. It has to be my shape, because I can't just flatten the graph out and go straight across. I have to be curved and smooth. So for this one, so for the extrema for this one, we do have a local maximum right here and a local minimum right here. So let's see here. Look at the key. So local minimum, oh, sorry. So I've done this work, but I don't want to recalculate it all out again. I would actually use my calculator to solve it. So actually, let's let the calculator solve it. So on a Casio, we're going to go to the graph. So we've got x cubed minus x. Draw. Oop, there it is. Okay, so same shape. So on a Casio, if you want to find a max or min, you hit G-solve, and then select. There's max for F2, min for X3. So let's find the maximum, and it'll find it. Boop, 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 right there. So there's a maximum at. So we've got a local max at the coordinate -0.58, comma 0.38. We've also got a local minimum, that's this point down here, so G-solve min of positive 0.58 on the x and negative 0.38 on the y. Zeros, we actually already found all three of them. The zeros are right here. So the zeros are at -1, comma 0, they are at 0, comma 0, and they are at 1, comma 0. Now, if you're talking about not necessarily the coordinates, you're talking about just the zeros, it'd just be the x values. So there's a 0 at -1, there's a 0 at 0, there's a 0 at 1. Because the zeros are referring to the y value. Related to the monomials for which it's built, so similar pattern. As I move away from the origin, it looks like x cubed, but close to the origin, it looks like -x. It's slanting down to the right. Okay, so polynomial of degree n has at most n-1 local extrema and at most n zeros. So for example, what's talking about here is this has degree 3, so it has at most 2 local extrema, which it does, 1, 2. There can't be any more. And at least 3 zeros, 1, 2, 3, which it does. Over here is actually the same thing, degree 3. So there's at most 2 extrema. This happens to have none, because 0 is less than 2. And it has to have at least 2 zeros. Sorry, at most 3 zeros. It happens to have 1, which is less than 3. So end behavior, in sufficiently large viewing windows, the graph of a polynomial and the graph of its leading term appear to be identical. So what that means is, if I take, for example, my guys here, so I do x cubed plus x, if x gets really, really big, this graph essentially just looks like x cubed. And the same thing's true for the other one. If I have x cubed plus, whoops, minus x, that, when x gets really big, it's just the same thing as x cubed. The reason this happens is because of these exponents. When x is small, like 1 or 2, 1 cubed plus 1, this plus 1 makes a big difference. But when x gets very, very large, if x is like 1,000,000, if I cube 1,000,000, that's a giant number. And it's so big that even adding another 1,000,000 to it doesn't change its value a whole lot. If x is almost infinite, this smaller value gets swamped. And that's true for everything. It doesn't matter how long your chain is. If I have 7x to the 6th plus 5x to the 5th plus 2x to the 4th minus 6x cubed plus 1x squared minus x plus 4, that's a 7 though, 7. The only term that matters when I'm looking at the end behavior is that. Because this x to the 6th, as x gets very, very big, swamps all the rest of these factors, especially the number. If you think about it, if x is 1,000,000, 1,000,000 to the 6th times 7, that value, if I add 7 to it, might as well be the same number. It's just going to be, this plus 7 changes this value by so little. But that's true for all of the terms other than the first. This value is going to change this one by so little. Okay, on the other side here, so this is leading term test for polynomial end behavior. So it gives you some generics. So for any polynomial function, blah, 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 the limits as x goes to infinity, so that's off the right-hand side. Limit as x goes to negative infinity off the left-hand side. The limits referring to the y value are determined by degree n to the polynomial and its leading coefficient. So this shape, you have a positive lead coefficient and an odd exponent. Over here, negative lead coefficient, odd exponent. Here you have positive and even. Here you have negative and even. So these dash parts here, the shape of the dash part depends on what that power is. If it's, so for example, if you really want to exaggerate this, so say I had x squared. Well, x squared looks something like this. X to the 4th potentially looks something like this. X to the 6th looks something like that. So I'm actually 1, 2, 3, 4, 5. The number of humps is always one less than the exponent at most. Doesn't have to be. The x to the 4th could also kind of be flat, like a U shape. But at the ends of the graph, they're all doing the same thing. They're both all climbing to positive infinity on both sides. And I keep doing this x to the 8th away from the origin looks exactly like x to the 6th, looks exactly like x to the 4th, looks exactly like x squared. So this dash part in the center here is affected by what the exponent actually is. These solid parts don't matter. Any even. Okay, so here we've got example 3. It says graph the polynomial in a window showing its extrema and its zeros and its end behavior. Describe the end behavior using limits. So I'm going to let my calculator handle the heavy lifting here. So x cubed plus 2x squared minus 11x minus 12. Zoom out. Need to zoom out again. So I'll try one more time. So let's find the extrema here. We'll find the roots first. So there's a 0 at -4. There's one at -1. And there's one at +3. So we'll jot these down. So -4, -1, and +3 are zeros. And extrema, so G-solve maximum. So we have a max at -2.6, comma 12.6. And find the minimum. The minimum occurs at 1.36, comma -20.7. That's pretty big. So drop our axes in here. So let's count by, we have to count by 2's in order to get these in. So -4, 0 is right there, -1, 0 is right there, 3, 0 is right there. So there's my zeros. I have a max -2.6, 12, so 2, 4, 6, 8, 10, 12. There's -2, so it's going to be about here. And a minimum at 1.3, so that's 1, and then down, way down here. So the graph looks like this. So end behavior, so the limit as x goes to infinity is positive infinity, it goes up forever. The limit as x goes to negative infinity is negative infinity. As I go left, the graph goes down. All right, so the next one down here, let's look at this guy. So, delete my graph. So 2x to the fourth plus 2x cubed minus 22x squared minus 18x plus 35. Okay, so let's try zoom auto and see what it does. Yeah, there we go. All right, so G-solve, let's find the roots first. So it's thinking. So there is one at negative 3, 0. I'm approximating here. There's one at negative 2, 0. There's one at 1, 0. And there's one at 3, 0. So that has to be it because I have x to the fourth and there's 4 zeros. So let's see if there's any maxes or mins. Oh yeah, negative 0.4, 38. Oh, because my y-axis is so crazy. Let's see if there's any more. Oh, that's the only one. G-solve minimum. Negative 2.6, negative 10.7. So there you go. So this graph is going to be real crazy to draw. So I'm not going to really try this super hard. So negative 3, negative 2, 1, and 3. So it goes like something goofy like that. Is a general shape, so it looks like. So as I go off to the right, I go to positive infinity. As I go off to the left, I also get positive infinity. This goes up. Okay, zeros of a polynomial. So find the zeros of this equation. So we're going to actually factor this. So we can factor an x out, which gives me this equation. We're finding the zeros, so we said equal to 0. This can still be factored. So two numbers that multiply to negative 6 and add to negative 1 are negative 3 and positive 2. So once you have it factored, you set each factor separately. Oops, lost my x. Equal to 0. So there's 1. X equals 0. This one would become x equals 3. This one would become x equals negative 2. So these three values will make that original equation equal to 0. So what I used there was called the multiplicity of a 0. Oh, sorry. Oops, not multiplicity. Multiplicity is how many times the zeros appear. That was the zero product property. So if f is a polynomial and x minus c to the m is a factor of f, but x minus c to n plus 1 is not, then c is a zero of multiplicity m. So a zero multiplicity m over 2 is a repeated zero. So that means you have the same solution more than once. Zeros of even and odd multiplicity. So it just says if 0 has an odd multiplicity, then the graph has to cross the x-axis at that value, meaning it changes sign. If the polynomial has a real zero of even multiplicity, then the graph does not cross. So if you look down here, so I have two zeros. I have x equals negative 2 with an odd multiplicity, because the exponent is negative, and I have a 0 at x equals 1 with an even multiplicity. So this one will cross the axis. This one will touch the axis. So the easiest kind of way to tell the general shape is to put these guys on a number line. So I'm going to pick 0 here, because 0 lies in between those two values. So if x is 0, this equation becomes 2 cubed, and then negative 1 squared, so that's going to be positive, that's going to be positive, so this section of the graph is positive. Since negative 2 is a odd multiplicity, this side of the graph has to be below the axis. Over here, since touch, it has to be above. So when I go to draw my graph, I want to sketch it real roughly. At negative 2 and at positive 1, I have to cross or touch the axis. So between negative 2 and 0, the graph is positive, so it has to do this. But to the right of 1 is also positive, which means the graph actually touches and comes back up to stay positive. At negative 2, it crosses over, so it just keeps going down. So this would be a very rough sketch by using the zeros and whether they're positive or negative. Without having to plug in individual values, I only have to plug in one if I use the zeros to get either side. All right, which brings us to the last page here, which is referred to as the intermediate value theorem. So the intermediate value theorem essentially just says that if your function is continuous, meaning it's smooth curve, no breaks, on some interval a to b, so these are both x values, then f takes on every value between f of a and f of b. So in other words, if y0 is between, please remember f of a and f of b are y values, so if you have some random y value between your two endpoints, then there must be some c value that generates that y value. And that c value has to be between a and b. If a and b have opposite signs, that means the graph has to go through the axis, because in order to get from a negative number to a positive number, you have to pass through zero. Now, in real world terms, what this kind of, if you want to think about, is like if you think about the speedometer on your car. As you start your car and start moving, you have 0 miles per hour. If you go up to the highway, 65, 70, however fast you're going, there is some point where you are driving exactly 37 miles an hour. Because in order to get from 0 to your highway speed, you have to pass through every number in between. So there is some place where you're going exactly 37. Might be for a split second, but it still happens. So it says, explain why a polynomial function of odd degree has at least one real zero. So this is because the end behavior is opposite. So one's going up, one's going down. So one's positive infinity, the other's negative infinity, which means you have to go through zero. Because in order to get from negative infinity to positive infinity, or vice versa, you have to pass through zero. All right, so here it says find all real zeros of the function. So I'm actually going to be lazy about this. You can graph it and let your calculator find it. So let's just do that. So x to the fourth plus 0.1 x cubed minus 6.5 x squared plus 7.9 x minus 2.4. Now there's not really a good algebra way to do this. So g-solve roots. So our solutions are, if I look at my graph, about negative 3.1. So there can be at most 4, because I have x to the fourth. Exactly 0.5. About 1.13. And there could potentially be one more. About 1.37. So those are my zeros, just from the calculator. Desmos will find them for you, et cetera, et cetera. All right, last one here. Dixie Packaging Company has contracted blah, blah, blah. So you want your volume to be 484 cubic inches. You're going to cut corners out of a 20 by 25 inch piece of cardboard and the flaps folded up. What size squares? So this is similar to a problem we did before. So you're cutting corners out of the square. So the volume of our box ends up being length, which is 20 minus 2x, because I cut 2 corners out, by width, 25 minus 2x, by height, x. But this needs to equal 484, because that's what I want the volume to be. So I can bring this 484 over. So 20 minus 2x, 25 minus 2x, times x, minus 484 equals 0. And if I do this, I actually put this in my calculator and just let it graph that, and I can use my calculator to find the zeros. I don't need to algebra it out. So let's see here. So quantity 20 minus 2x times 25 minus 2x times x minus 484. So your calculator doesn't care that you haven't FOILed that out. View window, nope. Zoom auto. There it is. Okay. So g-solve root. So 1.22. See if there's another solution. Or 6.87, if there's any more. Or 14.41. That's probably going to be it. Yep, okay. Now, so we get these 3 solutions. However, not all of them work. For example, it can't be 1441 because that's going to cut, that's more than half of my shortest side. So it can't be this one. So either of those 2 values actually should work. I could cut 1 1/4 or 1.25 inches off, or I could cut 6.87 inches off. So this one would be, if the cuts are small, the box is relatively flat, if the cuts are large, the box becomes taller. But both boxes have the same volume. So flat box versus deep box just depends on what you're looking for, because this box will be taller than this one will. And that does bring us to the end of this section.